So today our lecture is on permutation, n linear functions, determinant of partition matrix. So the different type of concepts, determinant, and we see what is the connection between this determinant and the matrix. Why this determinant? We know what is determinant, but why this determinant is such a thing? Why the definition of determinant is this? That is important. What is the role of this determinant in the whole scenario? So we'll see in this lecture what is the role of this determinant and why this definition of determinant is such thing, and why this n linear function is came out, and the one important thing is permutation. So what is n linear function? So n linear function is like that. So what is linear function? Linear function is say this function it's linear from a vector space to another vector space. If we know that this is alpha plus c beta is where alpha and beta from V and C is from the field f alpha plus c. What about the n linear? N linear means it is actually operates on n tuple. It's on n tuple, say v1, v2, dot, dot, dot. And it is linear on every coordinate. What is the meaning of that? Meaning is clear. For it is linear in every coordinate means say it is linear in the first coordinate. What is the meaning of that? Say if you say v plus c v1 dash, other coordinate is fixed, then it is linear on this first coordinate. That means it is v f of v1 v2 dot, 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 vn plus c times f of v1 dash v2 dot, 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 v. And same thing for every coordinate. If you on the ith coordinate say v1 dot, 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 v2 v I minus 1, and the ith coordinate is say vi plus c into vi dash, then vi plus 1 dot, 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 vn. If f operates on that, that is f of v1 v2 vn plus c times f of v1 v2 v I minus 1, then vi dash vi, then I plus 1 dot, 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 n linear. It's called n linear function. Now, what is alternating? It is, this is in determinant. The same things like that. Determinant also is an n linear function. If in some determinant, if the n rows are n minus 1 rows are fixed, and in the first row say you have say a11 plus c a11 dash, then a12 plus c12 dash, something like that. It is nothing but just a11 a12 a1n, then other rest are the same thing, and then c a11 dash c a12 dash, and c came out. We know the determinant one from one row, c is just came out outside the determinant, c into this just in the only one row. So this is n linear function. So determinant is a n linear function, but we define determinant as a linear function. We know if our determinant, what we know in our previous in class 12, this determinant follows this definition, but we are given the definition of determinant in this way. Say determinant is a function which is n linear, and then we will show our determinant in class 12 is same as this determinant what we define. One side is easy, the checking of one side is easy. If I assume our definition in class 12, we can easily show this is n linear, but the other way is tough. If I assume that is a n linear function, you have to prove this is the only one way we have to define is in our class 12. Define in class 12, that is the only thing, unique way that we have to define if some properties are there. So to prove this is tough. So if I assume our definition here, and if I assume in class 12 definition, from class 12 definition to our definition is easy, but from our definition to class 12 definition is tough. Why? Because sometimes it so happens that two equivalent statements, once from A to B it is say easy, but B to A is tough. That means B is apparently B has less information. but actually they are same information, equivalent. Apparently they are less. What is the meaning of that? That means the checking for B is some sort of minimal condition. Apparently less number of condition in B. In A there are several conditions. So that's why, since once we assume A, there are say 10 condition is there. This is called say square. If it is all sides are equal, all angles are equal, all angles are 90 degree, all diagonals are perpendicular, diagonals are equal, blah blah blah. These are definition. That means if I assume this definition, we can prove anything, any properties. All these properties listed. But if I say just okay, the square is thing, so all sides are the two consecutive sides are equal, and the diagonals are midpoint, intersect at the midpoint, and the angle is 90 degrees. If I say that's good enough to define square. Now from A, the previous definition, blah blah blah, everything is there. This is just trivial because it is one of the subset. But from this B, just our definition, actual definition of square, to define that the set of all list of all these properties is tough because you have to prove all these things. But to proving this is tough. Theoretically it is tough, but practical sense, the definition which contain less number of properties or less number of statement is more stronger. Why? Because in that case we have to check just a few conditions. Let's just assume if I want to prove something square, and then for the definition A, the list of all these 10 properties, we have to prove everything to prove A is something ABC is a square. You have to prove it is diagonals are equal. So you have to prove everything about this square. So working to work something with a square, the definition which contain all the properties, this is not easy. But just definition contain just it is only the actual definition. This is easy. So that's why if I assume our definition by class in class 12, that is something much there. But this definition, n linear function, the definition of determinant is n linear, alternative, and determinant of identity matrix is 1. We just assume this three, you can prove that this, assuming this three condition, we can prove that this is actually implied our definition in class 2. But that is tough. That part is tough. But once we can check it, after that, to show something is determinant, we no need to prove in class 12 the determinant. Oh, that means this function is output is a11, a222, a33, ann minus that no need of proof. We just prove it is a n linear, it is alternative, and it is a determinant of that f of I is 1. You just prove this thing, and you can deduce that, oh, this is a determinant. So that's why this definition of using this n linear function is easier to handle. But just in your life, one time, at least one time, you have to check whether really it is work or not. Is really the determinant in our sense in class 12. It's not only for the determinant. Is actually this happens in the several concepts or several term in the mathematics. There are two definitions basically in probability also. You have to take the minimum thing what is actually generate all these equivalent definitions. So you have to just you have to prove one time, but after that you never prove that. You just prove it is n linear, alternative, and determine that f of I equal to 1. So what is determinant function? Determinant function is just is n linear, alternating. Or what is alternating? What is just you know what is alternating. If you change two row, then you take a minus. So that means to swap two things. So if v1 v2 vn, if you swap just v of say v2 vi minus 1, and say it is vj, and then vi plus 1, or up to say I less than j, say vj minus 1, then vi. You swap these two, actually swap these two rows or two column, whatever. Then vj plus 1, whatever. This is just minus of this. This is minus of This is alternating n linear function. So what is determinant function? Is a n linear and alternating. If some n alternating n linear function. Oh, sorry. One more thing is this determinant must be determinant of I equal to 1. Because you can easily check if I assume that our determinant, so d function, say d of a is our determinant into something, so 2 into our determinant. This mod is our determinant in class 12, the right hand side. This also linear and alternating. This also linear and alternating. What is our determinant? Because d of I is not 1. So determinant function d of I must be 1. Now, this is great idea, great definition. But in our for practical purpose, to compute this. So now the question of computation. How do you compute the determinant? Then this the linear thing and this alternating and this determinant of I is 1. This does not help. This does not help. This help you for the proof, for the theoretical purpose, but really to compute something, this does not help. And it helps your class 12 definition will then help. It's a computation. So the two definitions also important. The both are important. One for the computational purpose, one for the theoretical thing. To deal with this definition in class 12, this a1, a2, and then minus of this theoretical dealing is very tough with that. And this linear thing theoretical is easy, but computation is not feasible. It doesn't help you. What will be the actual value of this, say 1, 2, 3, 4, this matrix? What is the determinant value? From just linear alternating and this, you can't just show. You can show basically, but it's work. It needs some work. So that's why the idea of permutation came. So this swapping actually, this once you swap this all this actually basically is called, say there is a 10. You swap these two. This is basically permute actually. It's a new permutation. First one is the identity permutation set. Next one is the new permutation is f of 1 equal to 2 and f of 2 equal to 1, and rest f of I equal to I for I greater than or equal to 3. So this is swap. So again a permutation. Again a swap. Change it. This is again a permutation. That means yours from any permutation to you can go to the another permutation. Just swapping at every step. You can easily go to that. Say if you from here, can you go there? Yes, we can go there. Say 6, 8, 9. Say then 3, 2. We can easily go to there. You have to check whether first you have to do 2 with 7. You swap to 2 to 2 with 7. Then we got 7. Then what about 2? Then 1 with 6. We got here. After some time, this algorithm terminate to this permutation. That means from every permutation, just using swapping, you get all permutation. Like in the graph, see if there is a set of all permutation, you know there are factorial many permutations, and each permutation like a vertex. And if you just join these two, if there is just only one swap, one permutation to another permutation, if you just one swap, one interchange, and you get the permutation, then you join this by edge, and this is actually a connected graph. Then maybe here to here also, maybe here to here. Actually, there are several swaps. Maybe here, but may not be from here to here. May not be this by swap. Only one swap. There is a least path actually. If it is from here to here, you have to go. You need the least path. Maybe other path also. You need the least path to go there, reach there. Now it is a connected graph. From every point you can go to every point, just using the only one operation, swapping. Now the important thing is, the interesting, not only important, it's very interesting. This from here to here, the length of this path, if it is even, every path is even. There is no odd path to go here to here, this vertex to this vertex. And if some vertex to this vertex, here to say you reach here by 3, then you can't reach there by any even number. That is a major result in permutation in modern algebra. I will not prove it here, but this is very interesting, very important and useful result in group theory, in permutations and in determinant. If you one from identity permutation, if you reach somewhere with even number of swap, if you reach there in the 4 number of swap, you can reach there with 6 number of swap. That is easy. We just it's the extra swapping 1 to 2, 1 with 2, again 1 with 2. You will get the same thing. Two operation will be actually cancel each other. The inverse to other. But it may happen if you reach from some permutation to another permutation with 10 swapping, it may happen it is not possible by 8. That may happen, but it's obviously possible with 12, 14, 16, but it's never possible with any odd number of steps. So we partition, we divide 2 parts, the all permutation. One is called even permutation, one is called odd permutation. What is this? The identity is the even permutation, and from identity permutation, even number of steps you reach the permutation is called even permutation, and to need odd number of steps to reach that permutation is called odd permutation. And if you from odd permutation, if you as you again apply odd number of swap, you will get an even permutation, and from even you will get a again even. So even then odd, it will be odd, odd then even, it will be odd, even then even, it will be even, odd then odd, it will be even. It's just add actually. If you go where something to somewhere to somewhere by 7 steps, then there to there by say 9 steps, you can go there by 16 steps, maybe less number of steps, other route of there, maybe obviously there are 18, 20 is always possible. You can just put some extra even number of steps which cancel each other. And what is the sign of the permutation? Say any permutation, actually we use this notation Sn. Sn is for this set 1 up to 2. Some author in some we also write this. This is actually this set. This box N is actually the set Sn. So this Sn to Sn bijection. Permutation is bijection. And this sign of this permutation is called either 1 or -1 if it is even and if it is odd. Now there is maybe composition, then tau, and you can easily check that sign will be your sign of tau into sign of sigma. If both are odd, then 2 composed of 2 odd permutation will be even. So -1 into -1 is 1. This is very important and interesting idea, sign of the permutation. What is the role of the sign of the permutation in determinant? You already observed for determinant, say say 3 cross 3 determinant. Is a 3 cross 3 determinant? What happened? We know that say A1, A2, A3, B1, B2, B3, C1, C2, C3. We know there are 6 terms, something like A1, B1, A1, B2, C3, blah blah blah, and there are 3R plus and 3R minus. And you know this one, if it is 1 to 3, it is plus. If it is A, B, C, say it is 1, 3, 2, then it is minus. Why? Because 1, 3, 2 is your odd permutation. Now you can write any n cross n determinant in this using this determinant, this sign and this permutation. How? Any n cross n determinant is nothing but if A, where A is Aij, it is just something sum is there and then product. So you first product and then sum. What is the product? You should take Ai and product over all I, and the second coordinate will be sigma of I, some permutation of I. And if you just from I to I equal to 1 to, that means you have a take only one element from each row, and since sigma is the permutation, you take only one element from each column, and you have to sum what the all permutation. There are factorial in many terms, and you have to multiply by sign of this permutation. This is a definition in 12th sense, but you have to prove at least in your life once. that n linear alternating, that function which take identity to 1, this actually match with this definition. Clearly, one side is easy. This the date function is actually n linear alternating, and this date of 1 is I is 1. Otherwise, tough. Now, this is actually role of permutation and sign of the permutation, odd even permutation in the determinant, and determinant has a great role in matrix. We will later see, but we'll in this lecture we'll slightly see different thing. We'll use some. This is not in actually linear algebra. This is in actually modern algebra part. Something about permutation. It's not directly used related with this linear algebra matrixing, but something is there. This is actually in the modern group theory part. So if it's only one chain, that is called two cycle. Two cycle means there is only one chain. Sometimes we write, say, some author also writes, say, 5, 6, say S6. So this, some author, we write this. This is means f of 1 is 2, f of 2 is 1, f of 3 is 3. But you don't, it is, you can write just 3, 2, 1, 3, 4, 5, 6. It is no need of writing 1, 2, 3, 4, 5, 6 above. 2, 1, 3 means it is the first position is 2, that means f of 1 is 2, f of 2 is 1. Actually, no need of writing this also. You can just write 2 and 1. What is the meaning of that? That means 2 and 1 is changed. Other rest are same. Now, say this is the one permutation. 1, 2, 3, 4, 5, 6, and then 2, 3, 1, 4, 5, 6. We can write this just 2, 3, 1, 4, 5, 6. But still, we can write it's like a cycle 2, 3, 1. What is the meaning of that? Rest are identity. 2 goes to 3, 3 goes to 1, 1 goes to 2. So f of 2 is 3, f of 2 is 3, f of 3 is 1, and f of 1 is 2. And this type of thing is called cycle. So permutation is something like that: 1, 2, 3, 4, 5, 6. Some are is 6 to 6, 5 to 5, 4 to 4. 2 goes to this one cycle. So that's why it's called cyclic permutation. But this is not a cyclic permutation. Say 1, 2, 3, 1, and then 5, 6, 4. This is not a cycle. Actually, this is a composition of two cycles. One is 1, 2, 3, another is 4, 5, 6. Composition of two cycles, two disjoint cycles. And you can just think, and you can prove, and you can observe that actually any permutation is actually either it is cyclic permutation or it is just a composition of some finite number of disjoint cyclic permutation. Because remember, this permutation is bijective. So one cycle you can't just go to the tree, cannot be like that actually. From one vertex, you can't generate two edge. There's always one edge inside, in degree is 1, out degree is 1. This is not possible because of bijection. That means it's actually disjoint cycle. Start from somewhere, you start from say 1, after some time you reach again in 1, this is the one complete cycle. And every vertex on this cycle can't go any other branch to outside the cycle because of the bijection. Now you have a cycle. If this is a complete cycle, it's cyclic permutation. And if it's not so complete, we take one more thing, one outside this cycle. There's maybe a single thing, maybe a single loop, and another cycle. You can just characterize all these permutations basically using this cycle. And this is called permutation group. Basically, this set of all permutations called permutation group is actually forms a group with this composition. Composition is just a permutation is a function, so this is a function composition. So it is called permutation group. And you can observe that all even permutation actually a subgroup. Odd or not, two odd composition of two odd permutation is even outside the set. But two composition of two even permutation is a even permutation. And this is called alternating group. something is called alternating group. This is called permutation group. It is called, say, A6 alternating group, and S6 is for the whole group. And obviously, this number of element of this is just cardinality. It's just factorial n by 2, because there are same number of odd permutation and even permutation is half. Factor n by 2 many even, factor n by 2 many odds. You can easily prove given a bijection from all even to odd. Just a single swapping, you just one swap, and this is a bijection actually, composed by a single swap. And this is an interesting example and interesting application of this all permutation thing is 15%. There is a in different mela there a game like that. This is a blank, this block is blank, and you can just shift this to this, then the 12 will be here and this will be blank. Or you can push 15 to the right. If you push down 12, then you can next step you can push 8 to that blank space, or you can just push 11 to the right, right? And after some time, can you reach there? This is the question. Using this change of some change, can you reach to this configurations? So you just swapping this 15 and 14. Can you go there? The question is, after some time, can we reach there in this configuration? Can we go from here to here? If someone asks you, so this is many years ago, this some agency say that if you can do this, I will give, say, 1 lakh rupees to you. But the answer is no, you can't do this. You can't reach from here to here. Why? Why you can't reach from here to here? And that means the group theory of this permutation, even outside. Why? You just observe. You just think there is a 16. Nothing is 16. That means for every step, you have to swap with 16. Every step, there is a condition. There is a swap. But the extra condition is, you can't swap 1 with 4. You can't swap 1 with 9, 14. You can swap with 16 to 12 in the first step, or 16 to 14. Oh, sorry, 16 to 15. If you swap with 16 to 15, then you can only swap 16 with 11, 15 with 11, 16 with 15, and 16 with 14. If you swap 16 with 15, it will just nullify the previous operation. But if you 16 with 14, it will new combination, new pattern, new configurations. Then you can change with 10 or 13 or 14. 14 means you are going path back within the graph. In the graph is just graphic, are just moving from the one configuration to another configuration. You just go one step forward and you just reverse the path. So we assume that there is no reverse. So after some time, after rotation, can you reach here? No. Why? Because every step you are actually using 16. Now think, 16 is after final step, 16 is came back to the same position where in the initial. Now to come back to 16 here, the number of times you go up must be number of times go down. Number of times go left must be number of times go right. The 16. There must be 16 must be involved at every step. Now to reach 16 here to final position, you need an even number of steps. You can't do it or an odd number of steps, because can't do it of number of steps to the same position 16, because every step 16 is needed. 16 is there. You can't interchange with 2 with 6. You have to change 2 with 16. after some step. So that means to reach here, if you can reach, is needed even number of steps. And we know if you swap everything, the even number of steps actually is a even permutation. But clearly this is an odd permutation. So you can't go this configuration by even number of steps because the odd permutation. So you can't reach there, as 16 is the initial position. This is a proof of this result. But it's very interesting. Unless you know this all this permutation thing and even odd permutation, this solution is not easy. You just can try, but you may never solve this because the solution not exists. And why does not exist? This proof is not, is a non-trivial, highly non-trivial proof. It just some elementary number theory, elementary thing, you can't prove it. You needs the even odd this permutation thing. And there is a determinant. You know what is determinant? Determinant function we already know, and we know how to expand this determinant. Is called classical adjoint thing. What is the cofactor and then adjoint? All of you know this. It is called adjoint of this aij. Say it is ai a11. So adjoint of this classical is called classical adjoint expansion. And we know this is a11 then a11. Classical cofactor technique is called adjoint, and then we know this. This is a determinant. But this requires number of computation, actually factorial n many things. So, and every time there is a n-1 many product. So there are factor n n-1 many addition and n-1 into factorial n. This is a high order multiplication is needed. So there is an expansion called technique called Laplace expansion. I'll just show it only 4 cross 4. You just divide 2 cross 2. Laplace thing is like that. You multiply this determinant with this. Then all sort of 2 cross 2 determinant with this 2 row fixed. You are changing the column. And with the, it's called minor of this thing. Like a minor of this element is this. So minor of any determinant is, you just cut off all this row as a column. So say there is a 4 cross 4, you are taking this determinant. What is the minor of this? This is cut off this, and you will get this, and this. This will be cut off. It's clear? There's 4 cross 4. This is a matrix. A determinant, take anyone, say if we take this, and this, the minor is of that is this, the green part. And now question of sign. What will be the sign? There is some sign notation. Is some sign is nothing but if you have this row is a ith row jth column, then if it's a 1 1, so you have sign will be -1 to the power 1 plus 1. Then it is 1 3, so it is 1 plus 3. It is 3 1, so it is 3 plus 1. Then it is 3 3, so plus 3 plus 3. So this will be a sign for this particular minor. And you just all sort of this time and then add sum, and this will lesser number of multiplication is needed. The classical expansion technique. If it's a 6 cross 6, you can do it. Actually, the optimal thing is 3 cross 3. And there's one more advantage. If there's something is called block diagonal matrix, something called block diagonal matrix is somewhere is non-zero elements are in some diagonal block, and these are rest are 0. In that case, if you take one block, you will just one block is enough in Laplace thing, because if you once you just change one more column without this gives zeros. So this is extra. So Laplace technique is then very useful. This at a glance you drop your, if it is a say total is a 10%, it is 3. This actually just a one line, it will step down to the 7 cross 7. And that is called Jacobi theorem. Just skip this Jacobi theorem. And there is some partition matrix, is block diagonal matrix. I already say the block diagonal matrix has, and if it's a partition matrix, something like this, the finding determinant is sometimes is easy with some extra condition. If there A is non-singular or D is non-singular, then you have some thing is something like that. AD is minus this proper determinant. Block diagonal matrix is also very find determinant is easy, and similar matrix, the similar matrix has the same determinant. Why? This is easy because we know the determinant of this by virtue of the determinant proper determinant. We know this is a product of the determinant is determinant of the product, and you will see obviously the V inverse exists, so it is non-zero. It cancel out. It's just 1 by this, and you will get this. So similar matrix has the same determinant. That means similar matrix, we know that from the previous class lecture, we know that similar matrix has some importance. In the similar classes, congruent classes, determinant will not change. So at least we find one property of the matrix which is not changed in the similarity thing. Is maybe true is non-similar, then also it is it may be same determinant. That may happen. Non because it may happen. Say is it B C A B. C is not inverse of B, but still the determinant of C is 1 by determinant of B. That may happen. So it is not that if the determinant is same, that the matrices are similar. That is not true. Converse is not true. But at least they are in the same similar in class, that a similar matrix, then have the same determinant. So up to this for today.